Hi, everybody. Let's start the lecture. So today we have, let's see how much we can do. I'm always more ambitious that I'm managing to do. The plan for today is to go over tree-based methods, then boosting, gradient boosting, and then if we can, multivariate vector autoregressions. But we'll see how we do. Okay, so these slides are based on the books by James Hasti and Tibshirani and Hasti, Tibshirani, Friedman. So these are considered to be classical books on machine learning. I actually used them for the previous lecture on Lasso, so I'm using them again. They are looking at the cross-sectional data. They are not concerned with time series aspects of the data, but nevertheless, this is the foundation. And then once you learn the foundation, it's easy to understand how this stuff works for time series. So let's start. We start with the decision trees, and to go over this, to understand the decision trees, we are going to be first we start decision trees. There are two sets of approaches in decision trees: regression trees and classification trees. And we start with regression trees, and then we will talk about classification trees. So first, regression trees. To explain the regression trees, we're going to use this data set that is called hitters. This data set is available on the author's websites. And by the way, both textbooks are available online for free. And they have been available for years. These are considered to be classic textbooks. So, and the hitters database is available along with the textbooks. So it has data on baseball hitters in the United States. It has a number of years a player had played in major leagues, number of hits a player made in the previous years, like how many times the player hit the ball, the salary in thousands of dollars. And this data set actually contains even more variables, but we will focus for now on only these three. And so we want to use the first 2 years and hits to predict salary. So here's a basic view on the decision tree, how it would look like if we apply a decision tree to the hitters data set. Imagine that somehow we divide the hitters into two categories, the ones who played in major leagues less than 4.5 years, and then the ones who played more than 4.5 years. And then for the ones who played less than 4.5 years, we say that their salary is in logs 5.11, and for those who played more than 4.5 years, we additionally divide them into two categories. One category with hits less than 117.5, and the other category is more than this number. And then for the first category, we say that their salary is 6 in logs, and for the second category, it's 6.74. So that would be an example of a regression tree. And we are not talking about here yet how we constructed it, but this is just an example what a regression tree means. Now, this how it looks in the real data. Here we have a two-dimensional space. On the horizontal axis, we have years. on the vertical axis we have hits, and this partition on this tree can be represented as partitioning this two-dimensional space into three subspaces. R1 for all of the hitters with years of experience less than 4.5, and then this other region, which is in its turn divided into two subregions. Then for each dot that falls into this region, well, sorry, for each dot in these regions, the observations that we have. Now, first, let us talk about how we built a regression tree, and then we will talk about all kinds of improvements and things like that. So, steps to build a regression tree. We first divide the predictor space. So we have a predictor space, which is given by a number of regressors x1, xp, where p can be any number larger than 1 or equal to 1. And first, we divide this regression space, which is a p-dimensional space, into j distinct and non-overlapping regions, R1, Rj. Then, for every observation that falls into a particular region, Rj, we make the same prediction, the mean of the response values for the training observation in Rj. So if we go back here, all the orange points here, observations that we have, and we calculate the average salary across these observations, and we come up with the number 4.11, and similarly for R3 and R2. Now, generally speaking, Rj can take any shape, but we consider only boxes. That's why, like, this regression tree can result only in boxes. Then the regions of the boxes are chosen so that the residual sum of squares is minimized. So we potentially minimize across all potential boxes, imaginable boxes that can divide the p-dimensional space into j boxes, and we calculate for each box we calculate the average value, and then we calculate the mean squared error. This problem is a very hard problem because there are so many ways how we can divide a p-dimensional space into j boxes. Moreover, we also need to choose this number j ideally, and so this is a just tremendously difficult problem generally. And the first simplification that we do when we talk about building trees, we take so-called top-down greedy approach, which is also known as recursive binary splitting. For that, so what we mean by top-down and by greedy. By top-down, we mean that we begin at the top of the tree with all observations belonging to a single region, and then successfully split the predictor space. This is why it's a tree. We're building a tree by splitting regions into subregions, into sub-subregions, and so on. And greedy in the sense that at each step, we make the best split at that step without looking ahead. That means that potentially splits that are optimal at a particular step can result in a non-optimal solutions if we were to reconsider the whole problem. Or another way to say the same thing is greedy means that we never change our decisions of the splits after we make them. We only go down and optimize only across the structure that we already built above. And then in the first step, in the very first step, we select the predictor xj. So we have j equal p predictors, and for each, the way we construct the breaking down into regions, in each state, in each step, we select first one predictor across this p predictors, and a threshold value or a cut point as such that the splitting the predictor space into regions R1 and R2 such that all observations with that particular feature predictor xj less than the threshold value go into one region, like left region, and the rest goes into the right region. And so we choose both the predictor and the threshold that minimize this objective function, which is the residual sum of squares across the two regions, where for the value of the prediction in each region, we take the average value across observations falling into this region. Then once we do the split, we fix it, and then we repeat the procedure. And we can be repeating this procedure forever until we perfectly fit the data. Obviously, we can do it, but usually, I mean, that would result, if we perfectly fit the data with such procedure, which we can, we are obviously overfitting the data, and this means that when we would need to make predictions using this kind of procedure, we will probably be doing a bad job. And so usually there are some criteria. We choose follow some criteria that allow us to tell us when to stop. And for example, one criterion can be that each region contains more than certain number of observations, like 5 observations. And once the regions that contain 5 or less observations, we no longer split. So that can be one criterion. Now, just a quick check of understanding. This breakdown of two-dimensional space into subregions cannot result from this greedy top-down approach or recursive binary splitting, because this region is not a box. Like this region is not a box, and such regions cannot result from a top-down approach. Also, this picture cannot result from a top-down approach because, for example, this region is not a box. So all regions have to be boxes. or they will, if we follow this procedure, all regions will be boxes. Now, here's an example that can result in a two-dimensional this recursive binary splitting, and the point of this example is to show that some regions we can be splitting twice over the same variable. For example, here we start by splitting the whole area using a predictor 1 with threshold 1, and so everything less than T1 goes to the left, and everything more than T1 goes to the right. Then if we look at the right branch, we again use the same regressor to make one more split. Now everything less than T3 goes into this region, and everything also less than T3 goes into R3, and everything more than T3 goes into this region, and so on. So in some situations, we can potentially split this region again and again, multiple times along just one variable. Then it would look perhaps like this. So these are possible outcomes where we're splitting multiple times across one variable. Now, this is how
Excuse
it would
me.
look. Yes.
Is it by default that the left branch answers like true and the right branch answers false?
This is just a visual representation. There's here, it's like there is no true and false, and you can follow any rule you want. This is just a mnemonics that people use. It's natural to have everything like smaller to the left, everything bigger to the right.
Yes, okay.
But of course, nothing will change if we flip. But that would be unusual because people are not used to. And also, we can use not only continuous variables like in this example, but we can be using categorical variables like, say, a color, blue, green, and then there is no real mnemonics. We just can be choosing whatever direction we want if these are categorical variables. But of course, when you will be using trees in your practical applications, you wouldn't even think about this because everything will be done for you under the hood by software packages. Now this, how it would look like in a three-dimensional space when of the two predictors and one outcome, like we divide the space first, say, along like this, then everything falling into this box is assigned a low value of y. Then say we divide it like this, everything in this region is assigned a higher value of y, and so on. Um, now there are problems with this procedure, and one of the problems that I already alluded to is that we can easily overfit the data. And especially if we are not careful with the stopping criterion, where to stop, when to stop, how to stop. And on the other hand, as always, if we are not flexible enough, we can be not doing a good job fitting the data. So if we use just one split, and that's our prediction based on just one split, then obviously that's a bad tree. And so we are having this, if we are doing just one split, then probably one split over just one variable, then probably we'll have low variance in the sense that if a new data arrives, this split and the prediction wouldn't change, but the bias will be huge. On the other hand, if you're building a complex tree, potentially, if the new data arrives and we are trying to rebuild the tree from scratch, that would result from a totally different tree, which means that there's potentially a huge variance in this method if the tree is too complex. So one idea how to not to build too difficult trees is, as I said, stop when there are only a certain number of observations in a tree in each region. No stop when there is a less than a certain number of observations in each region. An alternative procedure is to make a split only if the reduction in residual sum of squares exceeds some threshold. The problem with this is that we might stop at some node and we can have lots of observations in that node, and like a split on any of the variables now might not be giving a significant reduction in the residual sum of squares. But if we make one split, then later on we can achieve a huge reduction, potentially a huge reduction in residual sum of square if we split one more time on maybe some other variable. So we need to somehow overcome this short-sightedness problem. So people came up with this idea of tree pruning. You first grow a large tree, and then you start removing its leaves or like branches until you are satisfied with the outcome, until like you don't remove the branches that result in a significant loss of error. So the problem is, of course, it's not clear how to do this pruning. And so this is where we need some explanation. I mean, to be somehow a bit smart, how we will be doing the pruning. So here's an example of unpruned, relatively, it's not that large, but definitely bigger than 2 levels that we saw before. Now it has way more levels, and it involves way more variables. Like it still involves years of experience, hits, but it also includes other variables like walks, RBI, whatever that means, putouts. That doesn't matter what that means. I actually tried to learn while I lived in the States. I tried to learn baseball, but I never got into it. So that doesn't matter for us. So now with this big tall tree, we can prune it back by the following procedure. We start with the biggest tree, T0, and then suppose this one, n is the number of the terminal nodes, which here is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 terminal nodes. So in our example, n is equal to 12. Then given T0, we construct all possible trees with n minus 1 terminal nodes, but by removing a pair of leaves. So to do this, we say remove this pair of leaves, or this pair of leaves, or this pair of leaves, or this pair of leaves. So we cannot, here we are not removing leaves like this, obviously. So because they belong to different subtrees. We are removing leaves belonging to the same subtree. And that would leave us, like in this example, that would give us 1, 2, 3, 4 variants. And when we remove this leaf and don't change anything else, we replace this value. We put a value which is an average value in this subtree. We do the same here if we are focused on this subtree and so on. So we have now 4 different trees, and among these 4 different trees, we select the one that results in the smallest residual sum of squared if we apply it to say training data. Or we can be checking it on the test data. So we built it on the training data, and then we check it on the test data. And once we decided on which pair of leaves we remove on this step, we repeat this procedure to the modified tree. And so then we can, by following this procedure, we can go from the bottom to the up to the smallest tree by constructing a sequence of nested trees. So this would be our sequence of nested trees, where T0 is the largest tree, the unpruned tree, and Tm is the tree without any leaves. Then we can also, sorry, right, I didn't say it correctly. We decide which leaves to remove by checking the residual sum of squares on the training data. But then once we constructed the sequence of trees, we select the best tree based on the test data. By say doing cross-validation, if we are doing time series methods, then we are using this kind of expanding window error, and we apply all trees to that expanding window procedure, and then select the one that gives the best result. There is a way to describe this procedure in more compact terms by writing it as a minimization problem over the number of terminal nodes of the tree T. Sorry, we are minimizing over a tree by this loss function. Here we are for each tree, we have a set of rectangles corresponding to terminal nodes or regions. We are adding up our squared error across all regions. This value is the average value in the region, and we are penalizing it by the number of terminal nodes in the tree, with some penalty parameter alpha, which is a tuning parameter. If alpha is 0, so there is no penalty, then we will select the full tree that perfectly fits the data. If alpha is infinity, or very large number, we will select the null tree. Then one can show that for each alpha, there is a solution there is a corresponding tree from this sequence of nested trees that result from the weakest link pruning. And then we can choose the tuning parameter alpha by cross-validation. So by looking at this optimization problem, it just gives us an idea how we can do this optimization in a perhaps more compact way or more computationally feasible way than just building and then building trees and pruning. We instead can be solving this optimization problem, and once we have this optimization problem, potentially computer software can deal with it better, faster than with pruning. Now, there is a subtlety how you do cross-validation on trees. And let us first talk about the wrong way to do cross-validation. And I want to let's go through it, and then I want to ask you what's wrong with this. So the wrong way, construct a sequence of trees for a range of values of alpha. So choose like alpha on the grid, the same how we did with lasso or ridge, and then construct a sequence of trees for each alpha. Then split training data into k folds. For each tree, TI use every fold except for the case to estimate the average in each region. And then for each tree, calculate the residual sum of square in the test fold. So the way I explained it during tutorials, how we do the, it was during the second tutorial I was explaining how we do the k-fold cross-validation. So we divide our when we are dealing with cross-sectional data. This doesn't apply to time series data. So we divide the data set into k parts, and then say we use for each tree data in all, we sequentially throw away the first fold, then For each tree, we estimate the values in the nodes based on the remaining faults. Then we calculate the residual sum of squares in the fault that we left out. And then we repeat it for all faults. Then for each tree TI, we can average the k-test errors that are calculated on the faults and select alpha that minimizes the error. So what's wrong with this approach? Yes. Anyone?
Looks pretty logical, but still.
Do we calculate the RSS while taking into account the size of the region, the number of observations?
Yes, of course.
I mean, with the penalty that we talked about in the last slide.
Yeah. Right. Do we take penalty into account here? I think
shouldn't we get a lower error from the higher alpha always? Like no. I mean, if alpha is equal to 1, then we just perfectly classify all our observations.
So we are not dealing with classification here. We are dealing here with regression, right? But okay, so we are fitting. You are saying that if alpha equal to 1, maybe you mean alpha equal to 0. Or 1.
0.
Yeah, that would be on the training set, but on the test set, we will have some error. On the test set, the error is unclear how it depends on alpha. That's why we use the test set approach or cross-validation approach. Yeah, and we don't, right, for the Darius question, we don't, we calculate the residual sum of squares. We don't calculate this part.
Then it will be lower for overfitted trees, no?
No, but we calculate the error. We calculate the error on the test data set. So it doesn't necessarily, it probably will be high for overfitted trees. So we calculate residual sum of squares on the test fault. We use alpha when we are doing the split, the training, but then when we are calculating the residual sum of squares, we don't use alpha. on the test. Sorry, when we are calculating error on the test set, we don't use alpha.
Okay, so we need to find some other mistake, right?
Yeah.
Okay.
Why do we even splitting our data into false? Our training data.
Well, okay, forget so perhaps this is not a good terminology because I'm not consistent because the textbooks are not consistent because the literature is not consistent. One way of describing of what we are doing is we are splitting the data on train and test data sets, subsets. Another way is to say that we are splitting data in, train and test, and then each train and the train data set, we are splitting into k parts, and then we do k iterations on the train data set by calling one part a validation set and the remaining parts train data set. I don't know. So we can be, and then once we finished manipulations with the train data set by selecting some model, we can do selection of other models, or like not selection, sorry, training of other models on the same data set. And then we can compare the performance of a bunch of models on the test data set. So that's why there is a bit of a confusion with terminology here. But think about it this way, that we are splitting the data, the original data into k folds.
Okay, so the mistake is not in that we should test on the case fold either.
No, of course not. No, because this is the usual cross-validation approach. So how does it work?
No, I mean, it's written that we should calculate the RSS in the test fold, and I thought maybe.
No. Yeah, this
Okay.
on the validation fold.
Okay, and do I understand correctly that for each alpha we get M trees? So the trees are kind of in an inner loop, in the inner loop. And we select the best tree, and then we select the best alpha.
Yeah. So for each alpha, we select the best tree, and then we select the best alpha after that. So, but here the problem with this is suppose that I'm fixing alpha, like 0.1 or I don't know, 0.5 or 2. So the mistake is even if we fix alpha to some value. So just maybe even forget about this part and this part. But this, of course, this part is important, but that's not the source of an error. That's all I wanted to say.
Okay, and is the data ordered when we split it? Like sorted?
Is the data ordered? In what sense?
I mean sorted, because then some portion of values will not be available in the training set. But it might not be sorted.
It doesn't matter. So our observations are like y1, a vector of x1s, y2, vector of x2s, yn, vector of xn's. And then there is no sense in which, well, we might sort them over a y1, but a y, sorry, but it doesn't matter.
Give up.
Give up. So there is a data leakage here somewhere. That's a hint. Where is the data leakage here? Remember, we talked about during the last tutorial that we shouldn't do the data leakage is the number one.
Because in the RSS, there is the average for one set of like faults except for case and another set of faults except for case. So for every fault, there is some data in the RSS in the average of the k-test error, something like that.
Okay, how should we modify this?
Where is the leakage again?
Daria, where is the leakage?
Okay, as far as I get it, we build the tree and then we don't modify it.
Yeah.
And then we calculate different RSS. So, well, but we built the tree and we didn't modify it. So when we drop some portion of the data and re-estimate the RSS, the information that was used to build the tree is somewhere there.
Excellent. Yes. So this part is problematic. We built a tree for a given value of alpha. We built like a sequence of trees based on the whole data set. So somehow this should come first, and we should be like split the data set, test, train. Do the whole procedure on this part, calculate error on this part. Then choose this as a test. Leave it out. Again, do the whole procedure on the remaining part, test on the test, calculate the error on the test part, and so on.
You mean we need to recalculate our coefficients or
sequence of trees with everything, sequence of trees and the values on the terminal nodes, everything. We need to recalculate everything. Does it make sense?
So we'll have like 2 trees for test and for train samples, or not? To build
No.
a separate sequence.
The sequence is one for each. Okay, maybe it's like if you think about
the k-fold procedures should be the very the outer loop, the very first loop, right?
Sorry, say it again.
The k-fold procedure should be the first loop of all, and so yes.
Right. So if you think about time series, how you would do it in a time series, what this procedure tells you, like suppose we are talking about calculating, doing kind of analog of cross-validation on a time series data with expanding window estimation. So we would take some part of data, start, train, calculate error here. So build tree on this part, test on this part. Then expand, build tree on this part, test on this part. Sorry. Then, so test, then expand, build a tree, test, and so on. And then calculate the average error for each, and then repeat this for each alpha. That's the right way to do that's the analog of this procedure, of the right procedure for the time series data. Now, instead, what's written on this slide, the wrong way, says take the full data set, build the tree sequence, and then start testing it on this part, then on this part, then on this part, which doesn't make sense. It's, or I would rather say that calculate the averages in this part, then test on this part, calculate the averages in this part, test on this part, and so on. So this is wrong. Basically, this is the right thing. We first split the training data into k-folds. Then for each fold, we leave one fold out. Train for each value of alpha, we construct a sequence of trees, find prediction in each region of each tree. Then for each tree, we calculate the residual sum of square in the test set. And then we choose alpha that minimizes the average test error. So importantly, we are doing all the fitting, including the construction of trees, using only on the training data. Hopefully, once you see it, you say, yeah, how else would you do it? Hopefully. But it was a useful exercise to start with this wrong way so that you see that it seems like correct, but it's not correct. Understood? Get it?
Yes.
Okay. Okay, let me skip this. This is just an illustration. We will do this stuff during tutorials. Now we can apply the same procedure to classification trees. So we haven't talked a lot about, at all about classification. But let me just say that originally trees originated from classification, and the regression using regression trees came later. So and when you're doing classification, like suppose you want to, if you think about economic application, you want to classify if next quarter there will be a recession, or like GDP will go up or down, and that's the only thing you're not concerned with the size, you're concerned with up or down on prediction. So that would be your classification. You want to classify plus or minus next quarter based on the data that you have. That's your typical classification problem. Another classification problem would be you observe a person who is trying to borrow money from a bank, and the bank needs to classify that person. Is that person going to default or not going to default? And if the person is going to default, then no credit. If the person is not going to default, then credit is given to the person. So now and I want to talk about classification because once we move to the next section, boosting, we will start with classification. For classification, we do the same procedure. The only difference is how we calculate the loss. Residual sum of squared is a bad choice to do to calculate the error when we are building a tree. A natural alternative to the residual sum of square is classification error rate, which is given by this, which is the fraction of the training observations in a region that do not belong to the most common class. So for each region, we calculate the most commonly occurring class, and then the error rate would be the fraction of observations that don't belong to that class. That's it. This is what's written in math here. So that is a natural alternative. However, the problem with this alternative is that it's not sufficiently sensitive to tree growing in the following sense. If we have say let me like if we have let me just give me a second. So if we have k classes, like more than 2 classes, then say a situation when if we apply this rule and we have in some region like class 1, 3 observations, class 2, let's say, no, sorry, should have prepared it quicker. So if we have class 1, say 10 observations, class 2, 9 observations, and class 3, 1 observation, or like 0 observations, say, versus class 1, 4 observations, class 2, 3 observations, and class 3, 3 observations. These are very sorry, I'm keep confusing. So okay, if we have this, like class 1, 10 observations, class 2, 0 observations, class 3, 0 observations, or class 1, 4 observations, class 2, 3 observations, class 3, 3 observations. So in both cases, we will, the majority voting on the most commonly occurring class will be class 1. But obviously, these two situations are very different. In one situation, in the first one, we intuitively think that classifying an observation that falls into this region as belonging to class 1 is very good, while in the second situation, it's probably not so good, because we are kind of on the edge, and it's kind of not even clear which class is the best. And so somehow we want to capture this. Perhaps another, I can even write it, yeah. I can write it even in with two classes, like situation 1, class 1 gets 9 observations, class 2 gets 1 observation, or situation 2, class 1 gets 5 observations, or 6, class 2 gets 3 observations. So we would think that in the first situation, our classification as class 1 is more certain than in the second situation. So in order to take this into account, we usually use either Gini index or entropy. The Gini index calculates the dispersion intuitively, dispersion between the different observations, different classes in the region. So mathematically, this is written like this, where we are dealing with region M. We are adding up over classes K. And for each class K, we calculate the proportion of observations in this class in this region multiplied by 1 minus this proportion. So intuitively, this measures the total variance across K classes in each region. If all PMK are close to 0 or 1, then it takes a small value. That would mean that all classes are approximately the same. And for this reason, this measure is referred as the measure of node purity. A small value indicates, a small value indicates that a node contains predominantly observations from a single class. Right, if all values are 0 and 1 is very large, then this will be this will give a small value. And it achieves the largest value when we have all observations in the same proportion, all classes in the same proportion. So I'm spending too much on this, just some interpretation, it's written here. Hopefully it's clear what's happening here. The alternative is an entropy, which is mathematically given by this, where PMK is again the proportion of observations in region M class K. This measure is always positive because log of this is negative. Then dm will be small if all PMK are near 0 or near 1, but only one can be near 1. Only one class can result in PMK near 1 because all of them should add up to 1. So again, this is another way of measure node purity. Okay, let me skip this. This is not so important. So I just want to say that numerically, Gini and dispersion are quite similar, while so usually either would do. I see often just people using Gini. But then there's only one thing that, of course, when you will be again using it in Python, say, you will be just using a package that would calculate for you, and by default it would use Gini probably. But you just need to keep in mind that when a tree is being grown, then these measures are used, but when pruning, this measure is used usually because that's more like closer to the error in the intuitive sense. So this misclassification error. Because eventually, when we will be making a prediction, we will be making a prediction based on the most occurring class in each region. So eventually, this is the error that would matter for us. How on the, say, on the population, or when we are calculating risk. Okay, so let me see how much is left. Let me skip this example. And I want to talk a little bit about trees versus linear models. So a linear regression assumes the model of the form like so, where x regressors beta coefficients that we need to estimate. And usually we know that if the number of observations n is large, then the model, the estimator, has low variance in the sense that if we repeatedly apply the same estimator to different data sets, then we will be getting, of the same size n, we will be getting roughly the same result. Now, regression trees assume a model of this form, where 1 is an indicator function that observation x belongs to region Rm, and Cm is the value that we assign to that region. And even if the data set is very large, or especially when the data set is very large, as new data sets arrive, we will be getting very different regression trees. And this is a problem And so again, we talked about it, that we resolve this problem by pruning. Okay, and the bottom line is that you can view this the tree fitting exercise as minimizing your prediction, you can write it, or your predictor, you can write it in this form. That's another message of this slide, as if you compare it to the linear regression, then this is where your nonlinearity comes from, the division of the feature space into subregions. Here is an illustration. If we say have a two-dimensional example with x1, x2, and we want to do a classification, if the decision boundary is linear, so we want to do a classification to green and yellow parts, and if the decision boundary is linear, then a linear classifier would be the best, of course, and the decision trees potentially can do a really bad job, because how will we classify, like, I guess this, then this are the splits, and obviously applying a nonlinear classifier is really difficult here. While if the boundary is nonlinear, then applying trees would outperform the linear classifier. And the point here is that depending on what is the true boundary, one method or the other can outperform. So it can be the linear classifier that can outperform if the decision boundary is closer to the linear, and if the decision boundary is closer to the nonlinear, then the decision trees would outperform. What are the advantages of decision trees and disadvantages? So the advantages are that decision trees are easy to display, explain, and interpret. You can just build the tree and present it, and you know what's going on, why the decisions are made. The problems with them are that they don't have the same level of predictive accuracy, and can be very non-robust. A small change in the data can cause a large change in the final estimated trees. So it's a very nice idea, and trees are used a lot. That's why we start with trees, but they are used in a certain way, and we are going to discuss more today how they're used. But by itself, like the way I described, even with pruning, they are almost never used. So you need to know this, but you would probably practically, you would never use them the way we have just described. There are a couple of modifications that are useful to know, just because you're going through this machine learning class. But the biggest, the most important one will be boosting, and that would be the second part of today's, the second lecture today would be devoted to boosting. But we need to quickly go through two variants, bagging and random forests, that are also maybe useful in some contexts, but basically, practically, most likely you will be always doing boosting. Nevertheless, let me quickly talk about bagging. So decision trees suffering from high variance, it's an issue, and the bagging is a procedure to reduce the variance. The way it does, so if bagging is short for bootstrap aggregating, the way it does, it generates bootstrapped data sets, and I will describe in a second what that means. Then uses each of the data sets to fit a tree, and then, or actually any model, and then averages the outcome across all these trees. So this is actually a general purpose procedure. That's why it's useful to know it, because in some contexts it can be very useful. So the way to construct the bootstrap samples, if we have our set of observations, we take each observation, say their assigned numbers 1 through n, then we take each observation with replacement, meaning that with probability 1 over n, we take one observation, then we take, again with probability 1 over n, the next observation from the same pool of observations, so that one observation can appear, like observation 1 can appear several times in the sample, because we are taking it with replacement. This way we are simulating we are thinking about our sample that we have as representing the population, and when we draw from our sample with replacement, we are kind of thinking about this procedure as drawing from the population. Then we just, for each constructed training sample that we do by this procedure, we construct, say, the tree. Then we do it b times, say like 1,000 times, and average over the results, and that would be our prediction. This one note about this procedure is that when we are doing this bootstrapping, constructing of pulling observations with probability 1 over n, we can show that the probability that any particular observation doesn't get into a sample, the training sample, is given by this number. It's very easy to show. Then for large enough n, this number is approximately 2/3 sorry, yeah, to 1/3, that this number is approximately 1/3 for large enough n. Then that means that on average, the bootstrap samples from 2/3 of all observations. That means that on average, 1/3 of observations are left, which is a lot. Or 1/3 of observations are not used in our procedure. So we can be using these observations that are left as a testing sample, then gives us a way to calculate the test error. Uh, and then if we repeat this bootstrapping procedure many times, we can calculate the test error, and that gives us a way to compare different models. And we will work through the example during our tutorials. Okay, another point to make here is that, which is a more general point that applies also to boosting that we will study later today, is that it's when we are doing this bagging procedure, it's hard to interpret variable importance, which variables are important for the decisions that we make. And overall, this measuring variable importance is a big issue with machine learning methods that go beyond linear methods. But the good thing about the tree approach is that we can construct so-called variable importance measure. For example, for bagging recession trees, we can assign to each variable the total amount of residual sum of square that is decreased due to splits over this variable, average over all trees. And we can do a similar metric for classification. So here's an example of how that can look like, say, in the classification on some data set. Again, we will look at the examples during the tutorials, how these variable importance measures are constructed. They're useful to getting a sense what impacts the outcomes that we get. And finally, let me quickly talk about random forests. So in bagging, the trees are potentially correlated in the sense that we can be getting similar samples again and again that contain the similar set of observations, especially if they often occur in the population. Then that higher correlation between different trees results that gives us a smaller reduction in variance. So we don't achieve our goal of reducing the variance of trees if we're using bagging here. And here comes the idea of random forests that tries to minimize this problem. By this, the key here is random. As in bagging, we build decision trees on bootstrap training samples, but the difference is that each time when we do a split in a particular tree, we consider only a random sample of m predictors. Like if we have x1, xp, then every time we need to do a split, we first sample m predictors randomly, and then we consider among them which one would result in a better split with a better threshold. Typically, the value of m is a square root of p. Let me also skip this. It's just, I think the idea is easy enough. I just rushing through it because I want to see if it's not clear what I'm talking about. And then I want to start talking about boosting trees because this is the most important part of today's lecture. So let me know if you don't understand something because I really want to get to boosting trees.
And in bagging, approach, we don't choose randomly the variables, right?
No, we don't choose randomly, right?
We just take them all.
We take them all, yes. But
Yeah,
we, of
okay.
course, the random forest is just like a variant of Bayesian where we randomly choose some sample of variables.
Yeah, okay. It makes sense.
Okay, I rushed through it, but really, I think this is maybe it's not clear what I'm talking about for some of you, but really, I think this part is easy. Boosting is difficult, and that's where I want to spend more time. This part, you probably, if you just look through the slides, you would understand it. Even like very quickly, even if you didn't understand now. But boosting usually is considered to be very difficult. Okay, so let's take, let's say, a 15 minutes break until 11:20, and then reconvene to talk about boosting.
Okay.